I moved from the, let's say, official platform to my own computer because it seems that either me, I'm not very good at using the new platform, or we have some additional problem due to the system. So we will probably have to organize a test at the beginning of next week before the next lecture. No, I planned to go a bit further in the lectures, but there are basically 3 minutes left, and I will leave the floor to Josh, and I will restart next time. Just a few ideas. I started last time to enter into this topic. So embodied doesn't mean that the agent has a body, but means at least a number of things. That it is, first of all, we are talking of a system which has intelligent behavior, but is subjected to law of physics, because everything is subjected to the laws of physics. We have the generation of the sensory stimulation is through the interaction with the real world. If the behavior of the system change the external world, it's a complex dynamical system in the sense, also in the technical sense of a complex system theory, and perform morphological computation. We will go further in this idea along in the next lectures, assuming we can we manage to have them. But morphological computation is basically stems from the observation that part of intelligent behaviors are actually due to the morphological characteristics of the agent. The typical example is the insect eye, but the simple act of a human grasping something is actually based to a large extent of our walking is to a large extent based on the exploitation of the body dynamics and the corporal and morphology. Then it will be based on a large number of parallel loosely coupled processes. It has an asynchronous nature, and it basically couple the sensory motor system with environment. Typical example are the passive walkers, and we will come back on this. So the big issue is if we want to, because if you look to this kind of humanoids, you, on the one hand, you observe that they have much better, for instance, power consumption rates than fully activated humanoid. On the other hand, you don't know how very well to change speed, for example, of to turn. The big challenge would be to have a new humanoid based, partially soft, based on this kind of principles, working not worse than the standard the fully actuated humanoids that, for example, we have seen in the DARPA challenge. And I would say that since it's now 10, I will stop here, and sorry for the issues that we have the morning, and I will leave the floor to Josh Bonga.
Okay, thank you very much, Fabio. Can everybody hear me okay?
I can hear you.
Okay, all right.
So it's being really troubled as well.
Okay.
So thank you for accepting the invitation at this early hour, and I'm sure that you will give a very nice lecture. But as far as I know, I may have already heard, and it was very interesting.
Great. Thank you, Fabio. So
Thank you.
Fabio mentioned soft materials, and I think that's a good transitionary concept for my lecture this morning. What I'm going to walk you through is sort of the field of soft robotics as it stands now, and some efforts we have made to try and automatically design both the morphology and control. As Fabio mentioned, this concept of morphological computation is that computation in some regard can be transferred back and forth between morphology and control in different machines. And what we would like to do as we automatically design these machines is allow the search method, which in our case is evolution, to strike a good balance between embedding computation in morphology, or some computation in morphology and some computation in control. So that's the connection between embodiment, morphological computation, soft robotics, and the focus of my lecture this morning, which is evolutionary computation. So let's start with soft robotics. This is a rapidly exploding subfield in robotics. There are a growing number of reports in the literature of a zoo of different kinds of soft robots. Here are just a few samples from the recent literature. As you can see, they all have very different morphologies. Some of those morphologies are more exotic than others. And one thing I'd like you to note by this sampling of soft robots is that it's very difficult to apply traditional robotic control methods like inverse kinematics to these machines. So in these particular embodied machines, it's particularly difficult to optimize a control policy for these machines to get them to do something useful. So it's particularly in these non-intuitive domains where we might be able to apply evolutionary methods. So basically, the state of play in the field of soft robotics is that we're getting better at manufacturing different kinds of robots, but our ability to control them well is lagging behind. And that's the challenge that my group and some other groups have taken up. So our approach to automatically designing such machines is to use an evolutionary process. Fabio, could you let me know if you're able to see this video?
Yes, yes,
Okay.
I can see it.
Okay, so this is a snapshot of an evolutionary process that was reported on by a former student of mine, Nicholas Cheney, while he was in Hod Lipson's group at Cornell. And I think this video nicely illustrates the basic principle of evolutionary algorithms applied to robotics. So as you can see from this video, obviously, we're evolving simulated machines in this case. Although they are simulated, they are embodied. So the movements of the body affect the sensory values that are obtained at the next time step. So we have a feedback loop from action through the environment and back to the sensor array. So we're evolving these machines. At any time step during this evolutionary process, we have a population of machines with different morphologies and controllers. I'll just restart this video. As I mentioned, we have a population of these machines. What you're seeing in this video is simply the most fit robot in the population at that time or at that generation. And we have a very simple algorithm. Basically, we assign fitness to each individual in the population. Those individuals that obtain a lower fitness value are deleted in the population. And those that survive, we randomly choose one, make a copy of it, and when we make a copy, we introduce some random modification to either the body or the control policy. So very simple optimization process. You can see that this is operating on a relatively sophisticated simulation. What you're watching are robots that are simulated in the VoxCAD soft robot simulator. You can Google VoxCAD and download it and try it out yourself. VoxCAD takes a finite element approach to simulating these machines. You can see that they're made up of a large number of elements or 3D pixels or voxels. In this experiment, there were 4 possible voxel types. Red and green, you can think of these as muscle cells. So whenever a red cell expands, a green cell contracts, and vice versa. So that's the active tissue. In some of these machines, if you look carefully, you'll see there are a few voxels that are light blue, like you see here. These are soft passive tissue, so something like ligament or fat. And dark blue voxels are the soft robot equivalent of bone, so passive hard tissue. So in this evolutionary algorithm that you see here, it is optimizing not only the 3D geometry or shape of the robot, but also its material properties, the distribution of those material properties, and its control. So that's evolutionary robotics, where we apply an evolutionary algorithm to try and design robots. The next step after this evolutionary process, of course, is to then take one of these simulated machines and manufacture it. That's known as crossing the reality gap, taking an evolved simulated robot and transferring it to reality. That's a separate challenge, and I'm not going to talk about that today, but for those of you that are interested, please email me and I can point you to some places in the literature that describe that challenge. Okay, so evolutionary algorithms have come a long way since the simple bit string genetic algorithms in the 70s, 80s, and 90s. The state of the art, in my opinion, in evolutionary computation at the moment is what's known as CPPNs, or compositional pattern producing networks. They were introduced by Ken Stanley back in 2007. I'm just going to give you an intuition for how this particular evolutionary algorithm works. Instead of encoding solutions to a problem in a bit string, the individual genomes are encoded as networks, and I've just drawn a cartoon network in panel A here. This network has 3 nodes, X, Y, and G, and a single edge that connects X to G. So that's a 3-node CPPN. And what this CPPN is going to do is to take positions within some space, and it's going to paint either color or material or control policy or anything we like. It's going to paint material into that space. So below the CPPN, you see a 2-dimensional pixel array. This is the phenotype. The CPPN is the genotype, and then we're going to take the genotype and paint the phenotype. The way we do that is we go to the top left of this pixel array, take the X and Y coordinates of that pixel, supply it at the input layer of this CPPN at X and Y, and we then propagate the X and Y position down through the network like you would in a normal neural network. And the single number that arrives at the output neuron G, in this case, indicates the amount of gray that we paint onto that pixel. We then visit the next pixel. We take its position, input it to the CPPN, take out the resulting G value, paint gray onto that pixel, and repeat for every pixel in this pixel array. And by doing that, we paint a picture inside this 2D pixel array. You can see in this CPPN, because there's a connection between X and G, basically the more X there is, or the further to the right the pixel is, the more G it receives. So one of the properties you can see of CPPNs is that even though I created this cartoon CPPN at random, it produces a non-random pattern. It produces a horizontal gradient from left to right. When we're evolving these CPPNs, we have a population of CPPNs. Each CPPN has its own architecture and set of weights and connections. So imagine a second CPPN in the population that looks like this. Same number of nodes, but now a connection from Y to G. And if you follow the same logic that I just walked you through, where we take the position of each pixel in the pixel array, input it to the CPPN, receive the G, the amount of G, and paint that pixel, you see that you get a gradient along the vertical axis this time. We can also, in this population of CPPNs, the connections between nodes are changing. We can also add, evolution can add and remove nodes and edges, and it can also change the activation function inside individual nodes, not unlike how activation functions are changed in a neural network. If the activation function switches from the identity function to a step function, like you see in panel C here, then only pixels that have an X value above some threshold will receive some gray, otherwise they're left white. So we get a band pattern. We can also, instead of painting patterns inside a two-dimensional space, we can paint patterns inside a three-dimensional space by adding a third input coordinate, z, as you see in panel E here, and we can then paint patterns within a three-dimensional space. Over time, as we evolve these CPPNs, we tend to get more complex CPPNs, like the one you see in panel F now. And the picture that you see at the bottom is a real image produced by evolving populations of CPPNs. CPPNs were originally designed to mimic biological development. So in biological development, you tend to see as an organism develops gradients of patterns, repeating patterns, symmetry. So you can see some symmetry in this image in panel F. So unlike a standard genetic algorithm, a bit string, if you create a random bit string, you tend to get a random combination of elements in whatever your solution is. CPPN tends to bias evolution towards regular patterns. And by regular patterns, I mean patterns that contain gradients, symmetry, and repetition. So that's CPPNs. The work reported on by Cheney and his colleagues in 2013, they took these CPPNs and again painted within a three-dimensional space, like you see in this image, but instead of painting colors, they painted voxels and voxel types. So inside this empty cage, they visited each 3D position inside this cage. They input the 3D position they input that the 3D position at that point into the CPPN, propagated it through the CPPN, and in this case, the CPPN has two output neurons, presence and material. The first output neuron, presence, is a binary value, 0 or 1. If a value arrives there of 0, no voxel is placed at that position. If a value of 1 arrives at that output neuron, a voxel is placed at that position. If a voxel is placed at a given position, the second output node is queried, and that second output node, material, is scaled to an integer between 0 and 3, 0, 1, 2, or 3, which dictates which of the four materials that voxel takes on. We then move to the next position in this empty cage, input its 3D position to the CPPN, propagate values through to the two output neurons, query whether a voxel should be placed there, and if so, what should its material type be, and so on. So by doing that, again, we can construct, or the CPPN can construct, the three-dimensional geometry of the robot, and also its material properties and the distribution of those material properties. So we now have a CPPN which is painting the body of the robot. In this first experiment, there was a very simple open loop controller, so the CPPN was not painting the brain. As I mentioned before, the red voxels and the green voxels simply oscillate at a fixed frequency and amplitude, and they oscillate in antiphase with one another. Pretty simple setup. Okay, so that was the initial experiment of evolving soft robots in simulation back in 2013. As I mentioned, evolutionary algorithms have come a long way since the early genetic algorithms. It is now making its way into industry. So as just one example, Autodesk Research has now opened up a division called Project Dreamcatcher, where instead of designing an item by hand in CAD, you would instead set a series of constraints and fitness functions and Project Dreamcatcher would evolve an item that would conform to all of your constraints and maximize whatever your performance metrics are. So an example of an evolved device you can see in the right-hand side here. Okay, so that's evolutionary computation applied to soft robots. You get some very nice designs when you do that. Here is a similar approach used by Francesco Carucci and his colleagues in Italy. Again, you'll notice the red and green here, which is the active part of the robot. The light blue voxels, as you'll remember, are passive soft materials. So this robot is made up of a majority of passive material. Fabio mentioned the passive dynamic walker as a great example of embodied cognition or morphological computation. You can see that this particular walker here is the soft robot equivalent of a passive dynamic walker. Because of the 3D geometry of the robot and the distribution of materials across it, it's able to achieve quadrupedal walking with very little active material. Most of the coordination between the four legs is accomplished by this passive material. So this is just an example that evolution can discover robots that exploit morphological computation. Okay, I'd like to walk you through another experiment now. This is a more recent experiment by, again, Nick Cheney, a former student, and myself, and Vitas Sunspiral at NASA Ames, and Hod Lipson now at Columbia. This is an attempt to improve the evolutionary algorithm itself. This is our control algorithm here. Every colored line here is a particular species of robot in a population. So we have a large population now with robots with different morphologies and control policies. Some are related in species, and we've drawn those with the same colored line. What you'll notice is that most of the evolutionary improvement in the behavior of the robots happened in the first 100 generations. And then in the remaining 6,500 generations, there was no evolutionary improvement. So this has to do with, this experiment has to do with improving the evolutionary process. And Nick introduced two improvements over the basic evolutionary algorithm that I just described to you to improve this this process, to enable evolution to continue producing ever better robots, no matter how many generations we allow it to run for. Okay, so let me show you the first improvement. Let me start with this. Remember that we have a CPPN, which is painting the body of a robot. The first thing Nick did was to expand the genotype to include not one CPPN, but two CPPNs. The first CPPN paints the morphology in the way that I just described to you. It dictates the 3D geometry of the robot and the material properties of the voxels. And the second CPPN paints a control policy onto the robot's body. In this simple experiment, the second CPPN, the only thing it did is to, again, paint an open loop controller onto the robot. For each active voxel, the first output of CPPN2 is frequency of oscillation of that active voxel, and the second output value indicates the phase offset of the oscillation of that voxel. So now we have an open loop controller where we have oscillating active voxels, all with different frequencies and different phase offsets. So we separate morphology and control. What that means is that as these population of pairs of CPPNs are evolving through the population, or evolving through evolutionary time, a mutation to CPPN1 will change the body, but not change the control policy. And a mutation to CPPN2 will change a robot's control policy, but not change its body. Okay, that's the first innovation. We separate the evolution of morphology and control. The second innovation that Nick introduced is what he calls the idea of protecting morphological innovation. And I'm going to use a cartoon here to illustrate this concept. Imagine instead of a soft robot, we have a biped that you see in gray here. And imagine it has an embedded control policy represented by the circles and edges, which represent neurons and synapses. Imagine we have this particular robot with this morphology and control. It's a biped. It manages to take a couple of steps, but not very well. As Fabio mentioned, bipedal locomotion is a particularly challenging task in robotics. Imagine a morphological mutation occurs that lengthens the robot's legs. That morphological innovation is probably going to disrupt the coordination between morphology and control. So with the longer legs, the robot falls over earlier or travels more slowly. So we see a decrease in fitness when this morphological mutation occurs. Because of this decrease in fitness, evolution would usually discard this longer legged robot. But imagine that we instead protect this morphological change for a few generations. And let's imagine in this cartoon example that a few generations later, this longer legged robot experiences a second mutation, which now changes the control policy. And that change in control policy happens to reestablish coordination between this robot's body and its brain. And because it has longer legs, it's able to travel faster than its grandparent did, its ancestor 2 mutations back. So we have the original ancestor. A morphological mutation decreases fitness, but we protect it for a while, and its child eventually outperforms the grandparent. That's the idea of protecting morphological innovation. Why protect morphological changes? Because morphological changes often provide unique opportunities. So a robot with longer legs has unique opportunities if subsequent control mutations can exploit that opportunity. So if we put those two innovations into the basic evolutionary algorithm that I just described to you, this idea of separating morphology and control so that evolution can make changes to the body without changing control and vice versa, and we protect morphological innovations, you go from an evolutionary algorithm that stalls out after only 100 generations to this. And now we have an evolutionary algorithm that the longer we run the evolutionary algorithm, the better and better solutions we obtain. So again, remember that each colored line here represents a particular species of robot in the population. And by species, I mean a robot that has the same morphology. So if you look at the inset panel, at that particular time in evolution, there was a red robot or a series of red robots. They all have exactly the same 3D geometry and material properties. But within that species, there are robots that have different control policies. And by control mutations, we can see that the red robots get better and better and better and eventually become the best robots in the population. But while that process is going on, there is another robot species that has a different morphology. You can think of the red robots as the dinosaurs and the blue robots as the mammals, if you like. Initially, the blue mammal robots are not as fit as the red dinosaurs. They have a different body, and that different body provided some unique opportunity. So as the blue robots continued to evolve, as their control policies improved, those control policies were better able to exploit the new body of the blue robots, and they eventually exploited that body to the point where they became better than the red robots and drove the red robots to extinction, and the blue robots became the best robots in the population. So that's how thinking carefully about embodiment and the particular properties of morphology, which is that they can provide new opportunities for behavior, and creating an evolutionary algorithm that can exploit those opportunities gives us a much more powerful automated design process. Now we can design ever better robots with more and more, if we have more and more computational resources available to us. Okay, now I'm going to switch and talk about another innovation to the evolutionary algorithm. So we're going to go back to the basic CPPN algorithm, which paints patterns onto a 3D substrate. And we're going to introduce now on top, or we're going to introduce into that evolutionary algorithm an additional process, which is a simulation of biological development. So by development here, what I mean is that the robot's morphology is going to change slowly over its lifetime. It's in essence going to grow from an infant robot into a mature adult robot. And I'll show you how that works. When we introduce development, we now have a system in which there are 3 time scales of change, fast, medium, and slow. And I'm going to show you 3 videos that illustrate those 3 time scales of change. Let's start with the fastest one. This is the fastest one is behavior. This is the open loop controller. In this case, you see we use a very simple open loop controller, which simply oscillates all of the voxels in phase at the same frequency and same amplitude. So we have an open loop controller, which is the fastest time scale. At the medium time scale, we have development. And as I mentioned, development gradually changes the shape of the robot from the beginning of its lifetime to the end of its lifetime. And it does that by taking some of the voxels and making them bigger, and taking other voxels and making them smaller. If we take that fast time scale and the medium time scale that I just showed you and put them together, you get something like this. If you watch carefully, you'll notice that this robot actually speeds up and slows down over its lifetime, even though its open loop controller has the same rate of oscillation. So what you're observing when this robot speeds up and slows down over its lifetime are periods of positive and negative interference between the fast and the medium time scale. Positive interference results in the robot speeding up, and negative interference corresponds to periods where the robot slows down. If evolution is now going to act on populations of such robots, these short periods of speeding up and slowing down provide rich material for evolution to work on. So what evolution is going to do, let me back up for a moment to the medium time scale. What evolution is now going to do is paint onto these voxels. It's going to paint onto each voxel using a CPPN whether that voxel increases in size or decreases in size over its lifetime. So in essence, the evolutionary process is going to dictate the developmental trajectory or developmental change of the robot. So fast time scale, medium time scale, and now I'll show you the slowest time scale, which is evolution. So early in evolution, we have the robot you see in the top row. Oops, I'm sorry. At the slow time scale, we have the robot you see in the top row, which was the best robot in early generations. And eventually, that robot evolved into the robot you see in the lower row, which clearly moves faster than its ancestor. So we now have an evolutionary process, which again is evolving populations of robots, and it's painting different developmental plans onto different robots. And by doing that, evolution is able to expand over evolutionary time periods in which the robot travels faster, and decreases the time during which the robot travels slower, meaning that it gets a faster and faster robot. Okay, so this is what we refer to as Evo, Devo, Soro. So Evo, Devo, meaning the evolution of development, and Soro meaning soft robotics. So now we're evolving the development of soft robots. So just to show you in a little more detail how this works, what I'm going to show you is a comparison of Evo Devo to Evo, where we remove development. We want to see whether development actually helps us automatically evolve good robots. So in the Evo Devo case, for each voxel, so for the kth voxel, the CPPN paints 2 numbers, VK0, which is the starting volume of the kth voxel, And it also paints VK1, which is the final volume of voxel K. And basically the resting volume of that voxel gradually changes from VK0 to VK1 over the lifetime of the robot. And its volume is also oscillating at a faster time scale as dictated by the open loop controller. In this experiment, all the robots were 4 by 4 by 3 rectangles of voxels. So that gives us 4 by 4 by 3 and then 2 parameters for each of those voxels, which gives us a total of 96 evolvable parameters. We did 30 evolutionary runs using this setup, and we looked at the average fitness of those robots evolved using EvoDevo, and we compared that to a series of evolutionary trials where everything was exactly the same, except now we removed development. Now we have CPPNs that paint just one number onto each voxel, VK0, which is the static resting volume of the kth voxel. And again, the fast oscillation is dictated by the control policy. So in the Evo case, we have 48 evolvable parameters, and in EvoDevo we have twice as many parameters to optimize. And intuition would say it's going to take evolution longer to produce good robots in the EvoDevo case because there are more parameters to optimize compared to Evo. But the case actually does not look like that. It does for the first 4,000 generations or so, but after a while, the EvoDevo case is able to evolve much faster moving robots than the Evo case. So the horizontal axis here is showing evolutionary time, and the vertical axis is showing the average fitness of the robots in those populations of evolutionary runs, with EvoDevo in orange and Evo in green. Okay, so there's something about the evolution of development that makes it easier for evolution to find good, fast-moving soft robots. What are those fast-moving robots that EvoDevo found? Well, they look like this. They tend to start with walking robots, but as the robot's body changes over its lifetime, it discovers active rolling. So as this robot starts to roll, it's not just rolling passively, it's actually, remember, it's oscillating these voxels, which keeps the roll going. So you can think of development, if you like, as sweeping over one part of the search space. So in the case of, let me just back up a little bit. In the case of Evo, the green curve, basically one robot corresponds to one body plan, one morphology, and the robot is stuck with that morphology. In the case of EvoDevo, a single robot over its lifetime sweeps through lots of different morphologies as its morphology develops. So in essence, evolution has a broader palette of morphologies to play with as it's looking for good morphologies to solve the task. And that's the explanation for why EvoDevo tends to produce faster moving robots than the Evo robots. Okay. The last experiment I want to describe to you is some work conducted by Francesco Carucci, working with Cecilia Lasci in Italy. Francesco used a very similar setup to the one I just described to you a few slides back. We have a population of CPPN pairs. Each pair of CPPNs paints, the first CPPN in the pair paints the robot's body, and the second CPPN paints a control policy onto that body. In the experiment that I just described to you, we have development here, but the developmental process, how the kth voxel changes from VK0 to VK1, is not influenced by the environment. So this is ballistic development, meaning that development just unfolds in whatever way evolution told it to unfold. But biological development does not work that way. Development responds to the environment. So the simplest example of that is in plants. So the way in which a plant grows is dictated by light gradients. Leaves grow towards the light. And the root system grows in response to moisture gradients. The roots grow into increasingly damp soil, or they seek out damp soil. So what I'm going to show you in this third and final experiment this morning is how Francesco altered this evolutionary process to now allow development to respond to the environment. The way he did that was to add a third output neuron to the first CPPN, which I'm showing you here. You can see in panel I. So the first CPPN now, again, paints the 3D geometry of the robot's body. It paints the material properties onto the voxels. And then finally, it paints an ordinary differential equation, an ODE, onto each voxel. And that ODE is as follows. It dictates how the stiffness of that voxel is going to change over time. And the way in which the stiffness of that voxel is going to change over time is going to be a function of the mechanical load operating on that voxel. You'll notice that there's an alpha there. The alpha in bold there, that is a single number that the CPPN paints. So for one voxel, if a CPPN paints a positive value for alpha, a positive number, then we have that voxel that will stiffen, will become more stiff as more load acts on that voxel, and will become less stiff or softer when there's less load acting on that voxel. If in the same robot, the CPPN paints a negative alpha value onto another voxel, that other voxel will become more stiff when there's less load acting on it, and will become less stiff when there's more load acting on it, right? You'll have an inverse relationship between change in stiffness and the amount of load. Imagine further that there is a third voxel in the same robot, and the CPPN now paints an alpha of 0 onto that voxel. If you just pause for a moment and think about what that means, an alpha of 0 means that the stiffness of that voxel will not change, regardless of the load operating on that voxel. Okay? All right, so that's the evolutionary setup. Francesco ran some evolutionary experiments and found this particular robot, which I'll play a few times for you. I'll just pause for a moment. You can see it's a relatively simple robot. It's got sort of one front leg, and that front leg oscillates and pulls the robot forward. At this point in the simulation, red voxels represent voxels that are experiencing more load, and green voxels represent voxels that are experiencing less load. And as you would imagine, obviously the voxels that are in contact with the ground are being pressed by the ground and experience increased load. Okay, so here's this one evolved robot. What Francesco did is that he took that evolved robot, played it back, and now he exposed it to an environment that it had never experienced during evolution, which is double gravity. And if you watch carefully, you'll see Francesco doubling the gravity. The minute he does, the robot stops moving because it's never experienced this environment before. I'll show you this transition again. But you'll notice something interesting. In this new environment, voxels around the edge of the robot begin to stiffen, and voxels in the interior of the robot soften. So this was a pretty surprising result to us. In essence, what this robot is doing is spontaneously growing an exoskeleton in a novel environment. As you can imagine, in twice the gravity, there's more mechanical load operating on this robot. But if all the voxels became stiff, the robot would become one solid skeleton and would no longer be able to move. On the other hand, if none of the pieces got stiff, the robot would remain sort of a blob of jelly lying on the ground. So evolution has discovered this unique evolution has rediscovered a solution that biological evolution discovered, which is a truss or a solid frame, but allowing the soft material to actuate that frame. So the reason I wanted to show you this video is that by adding in this unique form of development, we can not only evolve better robots, but we can evolve more robust robots. Evolution is able to discover sets of ordinary differential equations that allow the robot to change its body and material properties in the face of different environments. Now, admittedly, this is just one robot, so this is only anecdotal evidence of this robustness, and we're continuing to work on this and understand the principles behind it. It's interesting to note that this spontaneous development of an exoskeleton is very much like a common process known in biology, which is Wolff's law. Wolff's law says that the more pressure that acts on biological bone, the stronger or more bone will develop or will grow. So in essence, your skeleton strengthens at particular points of pressure and stress. So Wolff's law is an example of how biological body plans or morphologies respond and adapt to the environment. I'd ask you to think about all the robotics papers you've read in which you've seen Wolff's law mentioned. I'm willing to wager that most of you have never seen Wolff's law reported in a robotics paper or an AI paper. But how many of you have seen Hebbian learning reported in a robotics or AI paper, which is basically just neurological change in response to the environment? It sort of points out one of the blind spots in our field, which dates all the way back to René Descartes 300 years ago, which is we tend to focus on the soul or the mind or the brain, if you like, all the way through to modern emphasis on neurological plasticity. But there's very little emphasis in our field on morphological plasticity, getting the body to adapt to changes in its environment. So there is this sort of philosophical blind spot that we all have in the West because of Cartesian dualism. But I think it points to an opportunity for all of us working in robotics to really think about how we can exploit the body in the face of environmental change. I see that I have about 5 minutes left, so I'm going to just wrap up. All of the code to replicate these experiments is available at this URL. I'll leave that URL up for the next 5 minutes. I introduced you to a method for automatically designing soft robots. This was originally introduced by Nick Cheney back in 2013. I introduced you to the state-of-the-art in evolutionary computation. These are CPPNs, which can paint regular patterns in space. If we evolve populations of CPPNs, we can evolve regular patterns in space. I've shown you that if we evolve morphology and control independently, we can greatly increase the power of our evolutionary search process. And finally, if we introduce development, then we can now evolve regular patterns in time. We have robots that change their bodies and control policies over their lifetime. Okay, I'd like to thank UVM, my home institution, the Vermont Complex Systems Center, the United States National Science Foundation for funding some of this work, the U.S. Army Research Office, and NASA for also funding other portions of this research. So I think I will conclude my talk there, and I'm happy to take questions. Thank you very much.
Thank you very much, Josh. I think that actually Josh exemplified perfectly several of the main concepts of our course, because this is an example of synthetic methodology. For example, the fact that Evo-Devo, so putting together evolution and development, in some way speed up evolution, I think it's extremely interesting. And this is just one of the interesting thing that Josh and inspiring things that Josh thank you. Just to introduce, I have a question.
Okay.
you say that you have shown that dividing the evolution of morphology and of control speed up again evolution. So isn't this a kind of a Cartesian dualism entering from the back door?
Aha, it's a heresy, if you like.
Heresy.
That's yeah, that's a good observation, Fabio. So what we're trying to do is we separate them in the genome, which allows evolution to make changes to one or the other. But of course, in the phenotype, which is the robot in this case, there is no separation, right? They're connected together. Changes to the morphology have impacts on control, and changes on control have impact on morphology. So this is not Cartesian dualism because they are still equally important and they still have a very intimate interdependence in the phenotype. But it does suggest that in the genotype that evolution needs to be able to alter one while not disrupting the other, and vice versa. But again, this is just one experiment using that approach. It would be we're continuing on with that work to understand the implications of separating them in the genome.
No, that's interesting because there could be something that so exactly in the genotype of some system, or for instance of a Drosophila, maybe there might be that division. So it's interesting.
Thank you.
Under that respect. So it's could be interesting to see if it. But of course, no, it's very nice. No, I just wanted to be a bit provocative. So. So are there questions from the global lecture hall?
There's a comment here in the chat that the Moscow group could not see the presentation. I hope, oh, they say now they can see it. Oh, okay, that's fine.
Well,
happy to take any questions if anyone has any.
Because I think that Josh's work is really an example of what we are looking for. And you see that there is a lot of work to be done. So in particular, for those of you who are interested in research, I think it's extremely inspiring, because
hello?
I don't know if anybody, so probably you knocked out the audience.
Perhaps.
Information into.
Can you hear me? I have a question.
For you? Yep.
Yes.
Okay. Are you?
Go ahead.
Are you only working on this from the theoretical point of view, or are you also working on the mechanical development? Because I think nowadays it's very challenging, the physical construction of soft robotics.
I'm sorry, unfortunately the volume on your question was very low. I'm not sure if there's a way to increase the volume on your microphone.
Can you hear me better now?
That's a little better. Yeah, go ahead.
Better?
Yeah.
So I was questioning you if you are only working on the theoretical point of view of soft robotics, or if you are also working on the mechanical control, because as far as I know, the mechanical development of soft robotics systems, it's very challenging.
Yeah, I think I heard your question. So your question was whether we work on only the theoretical and simulation side, or whether we also work on the mechanical side. My research group is in the computer science department here at the University of Vermont. So our area of expertise is the simulation and theoretical side. We collaborate with a number of other research groups that are actually manufacturing these robots. One group is Hod Lipson's group at Columbia. They're making they've had some very exciting recent advances in printing soft robots. So if you Google Hod Lipson, you can find his group and see some of the work they're doing. We've also started a collaboration with Rebecca Kramer. She's a faculty member at Yale, and she's been developing some very interesting ways to manufacture soft robots in a simple manner. Most of the current manufacturing processes for soft robots are very complex, have to deal with very exotic materials, which is okay, but it would be nice if there was a simple way to create soft robots. And I think she has some very exciting ideas about that, and she's just about to publish her manufacturing process for that. So I'll leave it to Rebecca to reveal her methods. But there are a number of research groups here in the United States that we collaborate with that actually are attempting to manufacture some of our evolved simulated soft robots. It's a very good question. Thank you.
Thank you.
So are there other questions? So if not, I think that Josh will be happy also to answer privately and offline through email or other methods to your questions, for sure, through email.
Sure, yeah, please do contact me. I'd be happy to follow up with anybody about any of these concepts.
Because I don't want to repeat it again or to be too much flattered with my friend Josh, but I really think this approach, those approaches are very stimulating. Of course, as it was noticed, it's a challenge also to implement them physically, but I mean, it's a work for the next 10 years.
At least.
So it's very positive to see that we are not going to be unemployed soon.
This is true. Good to know.
So I thank again Josh for this exciting and inspiring talk and for the physical effort that he put in it, because this is our now traditional Vermont night lecture on future robotics, if you wish.
That's right. Thank you, Fabio, and thank you all for your time and your interest. Good luck with the course.
Okay, goodbye everybody, and see you next week.
Bye-bye.
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 Yes, next week we will update with the guest lecture program the website soon. I anticipate that next week the guest lecture will be by Olivier Michel from Cyberbotics on a new online tool for simulating robots that have been developed in Switzerland, and it's going to be widely used in the future. So thank you again for participating in these lectures. Accept my apologies for our apologies for the bumpy start, and see you next week. We will try to organize some point-to-point tests and also to some tests here, because as you notice, we finished with good old-fashioned laptop computer approach, while we have an expensive infrastructure that didn't work very well, but we will need to do some more tests. So thank you, and see you next week. We are going and check the website in a few days to see the full program of the lectures. Bye, everybody.